Good morning, students. In the last video, we have done some effects of refraction. We have done the effect of refraction on the speed of light. So if you remember, speed of light decreases when it travels from rare to denser medium. Okay, what was the formula? Formula was V equals to C upon mu. Means that speed of light decreases mu times or from the factor mu with respect to speed of light. So from this equation you can see that the speed of light decreases by the factor mu. Second effect was that frequency remains constant while the light changes the medium. Now it's time to check what will be the effect on the wavelength of light. Okay, so third effect, it is effect on wavelength of light. Okay, what might be the change occur when light travel from one medium to the another. Suppose this is a medium 1 having speed, let's say v1, frequency f, and wavelength lambda 1. This is medium 2 having speed v2, frequency f, and wavelength lambda 2. Light is coming like this, and let's say it is bending toward the normal. Fine. Now we have to check. Let's say the refractive index of medium 1 is mu1 and that of refractive index of medium 2 is mu2. What is the formula which relates the frequency, wavelength and the speed of light? So frequency, that is f, is nothing but v upon lambda. Frequency equals to velocity upon wavelength. Now if you check for medium 1, let's say the medium 1 is air or vacuum. Okay, we have considered this air or vacuum. So in this case, the speed of light, that is v1, it will become equals to c, right? And the value of mu1 will become equals to 1. So we will apply this value later. Okay, now f equals to v upon lambda. So for medium 1, f will be equals to v1 upon lambda 1, and for medium 2, f equals to v2 upon lambda 2, right? Okay, now why I have written on both side f, why not f1, f2? Because you know that frequency do not change while light changes the medium. So in the first medium frequency is f, so similarly in the second medium also the value of frequency is f. So equate them. When you equate them, you will get v1 upon lambda 1 equals to v2 upon lambda 2, right? Now let v1 is equals to c. As I mentioned here, v1 is equals to c. Why? It means the medium 1 is air or vacuum. Lambda 1 is equals to lambda, right? And v2 is v and lambda 2 is lambda dash. We just change the we can say denotation of the quantity, but we can say that there is no change in the concept or no change in the result. We just change the medium, nothing else. So what will be this equation now? v1 is nothing but c upon lambda 1 is nothing but lambda equals to v2 is v and lambda 2 is lambda dash. So basically we have to find the value of lambda dash. That means see how much wavelength change while the light changes the medium. So lambda 1 can be written as lambda into V upon C. Okay, let's say this is equation number 1. You know that V is nothing but C upon mu. Okay, that means therefore 1 upon mu can be written as V upon C. That means 1 upon C can be replaced by 1 upon mu. Okay, so put this value in equation number 1. What you'll get? You'll get lambda dash equals to lambda upon mu. So this will be the change in the wavelength of light. Lambda dash will be lambda upon mu. That means the wavelength also decreases by the factor mu. Okay. Now let's talk about the next topic known as reversibility of light. So what does it mean? Reversibility basically, as the word implies, that light is returning from its path, right? So what does it mean and what is significance of this topic in refraction? Let's see. Suppose this is an interface line, boundary between two different mediums, and this is our normal. The light is coming from, let's say, medium 1 here, and let's say bend toward the normal like this. You know, light bend toward the normal when light goes from rear to denser medium. So let the refractive index of medium 1 is mu1 and that of medium 2 is mu2, and the angle of refraction is I. Here angle of refraction is R. Quite simple. It's simple ray diagram of when the light suffers refraction. Now when light is going from medium 1 to medium 2, when light going from medium 1 to medium 2, how do we write? So according to Snell's law, according to Snell's law, that is equals to sine I upon sine R equals to, light is going from 1 to 2, that means 1 mu 2, equation number 1. It's simple. Now let's see, suppose I have placed a plane mirror perpendicular to the refracted ray. So what will happen? Light, this refracted ray, strike the plane and returns to its path. So light reflects from this plane mirror and retraces its path. It retraces the path. It means it continue the path from where it is coming, like this. Now in this case, after reflection, light is going from medium 2 to medium 1. Light is going from medium 1 to medium 2. Now according to Snell's law, now this R will become angle of incidence and the I will become angle of refraction. So according to Snell's law, what will be the new equation? That will be sine R upon Sin I equals to 2 mu 1. This is equation number 2. Multiply these two equations. So when you multiply these two equations, we'll get sin I upon sin R into sin R upon sin I equals to 1 mu 2 into 2 mu 1. So they will cancel out. So what we'll get? We'll get 2 mu 1 equals to 1 upon 1 mu 2. Now what is this result shows? It helps you to find the refractive index of one medium with respect to the another. For example, suppose you have a refractive index of one medium with respect to other. Let's say it's 1 upon 1.5, right? So 1 mu 2 is 1.5. It says find the value of refractive index of medium 1 with respect to 2. That means you have to find the value of 2 mu 1. So how do you find? Just reciprocate it. So value will be 1 upon 1.5. So basically this is the result. This result help you to find out the refractive index of one medium with respect to the another medium. Now let's talk about the refraction when the light passes through a thick glass plate. Refraction of light through a thick glass plate. Let's suppose we have a thick glass plate like this. Okay, let's say this thick glass plate is A, B, C and D. Light enters from the surface B. Okay, so let's see, this is the incident ray. Okay, and this will be normal. Like this is O, this is A. So AO is the incident ray. Now what will happen, because the light going from, let's say, air to glass, it will bend toward the normal. It will go like this. The angle of, let this is N dash, angle of incidence is here I, and the angle of refraction is here R. Right. Now because you can see that these are two parallel lines, N dash and let's say M dash. So this angle will be again R, because there is no bending of light, is exactly straight. Now when light, this OB is refracted ray, right? I am writing here AO is incident ray. Incident ray. OB is refracted ray. Right. Now light will emerge from the surface CD. And how it will go? Because now light is going from denser to rare medium, it will bend away from the normal. But before we draw the emergent ray, let's see, if this glass plate was absent, then what will be the path of this incident ray AO? It will go undeviated like this. It will go undeviated like this. I have shown this ray, let's say A and E. A is the undeviated ray if the glass plate is not present, but actually it will not happen, because light suffers the refraction here, and when it comes out from the this plate, it will again suffer refraction. It will bend away from the normal. It will go like this. Let's say B and C. Now this, the angle between the emergent ray and the normal will be known as angle of emergence. Here BC is emergent ray. There is a result in this experiment that when light comes into the medium after so many refraction, then the angle of incidence is always equal to the angle of emergence. Here angle of incidence I will be equals to angle of emergent. It means the ray BC is parallel to AE. It means incidence ray, incident ray and emergent ray are parallel to each other. But as you can see in this diagram, they are not coincided. There's some distance between the incident ray and the emergent ray. Let the distance is x. This distance x, that means a parallel shift of the parallel shift between the incident ray and the emergent ray. This is known as lateral inversion. So this parallel shift between the incidence ray and the emergent ray is known as the lateral inversion. Now, what are the factors on which this lateral inversion depends? Let's talk about this. Factor affecting lateral inversion. First, this lateral inversion, that is this parallel shift, is directly proportional to the thickness T of the glass plate. This. That means if we increase the thickness of glass plate, the parallel shift between the incidence ray and the emergent ray will be increases. Second, this parallel shift is proportional to the angle of incidence. That means if we increase the angle of incidence, then again the parallel shift will be increases. And third, it depends upon the relative refractive index of the glass plate. More will be if the refractive index of glass is more with respect to the medium width from the light is coming, then obviously the refraction will be more, hence there will be more shift between the incident ray and the emergent ray. So this is your lateral inversion, and what are the basic factors which affect the lateral inversion. So I think it's enough for today. We'll discuss some conceptual question and the other concept of the refraction in the next video. Till then, thank you so much, class.